Well, hello everyone. Welcome to my presentation on WebAssembly beyond the browser at JSWORLD Conference Online. And a very quick introduction about myself. I'm Shivay Lamba. I'm a developer advocate at Millisearch, which is a Rust-based search engine. And I'm also a WebAssembly ambassador. And if you want to connect with me, you can connect with me on my Twitter at @hardwareup. So without wasting any further time, let's get started. Now, first, let's also introduce what exactly is WebAssembly. So, as the word suggests, right, that it's based on two different words, web and assembly. But in reality, it's neither web or assembly. Essentially, you can think of it as an efficient low-level bytecode, which is usually generated by being a compilation target for other such kind of programming languages like C++, Rust, and even any other programming language for that matter, including scripting languages like Python, or let's say functional programming languages like Haskell, which can be used to convert the modules or functions written in those languages into this WebAssembly bytecode. So it's essentially a compilation target. Now there are some very nice benefits that basically comes with the WebAssembly bytecodes because they are portable, so that means they can work with any type of system architecture, whether it's x64 or x86, or even for that matter a number of different host environments. And they are also extremely secure because of the way the security sandbox model for WebAssembly modules works. And since they are also language agnostic, you could take a number of different languages and then compile them down into the WebAssembly bytecode with the supporting toolchain that helps to do so. So they are very efficient, they are portable, and of course, they are language agnostic. So that's why they become extremely beneficial whether you're running them on the browser or whether you're running them on outside the browser. Now, here's an example of how, let's say, a Hello World program might look like in WebAssembly. Now, within the entire WebAssembly format, strings as a data type are not supported. So this is an example for, let's say, printing an integer. But you can see that, of course, in case you wanted to write a program directly in WebAssembly, it's not usually advised. So that's why in most of the times, you will see WebAssembly bytecode as a compilation target rather than having to write the code yourself in WebAssembly. And typically, WebAssembly did start as a browser technology way back with the introduction of assembly.js. And one of the major reasons why it was needed was that JavaScript as a technology itself is not very powerful as a language. And especially when it comes to capabilities offered in other programming languages like C++ or even Rust, those capabilities simply do not exist in JavaScript because of some of the limitations, including the limitation of multi-threading. In order to circumvent or in order to overcome some of these issues, we thought of being able to, let's say, run programs or functions written in C++ in the browser. But the browser only supports JavaScript out of the box. And that is where the concept of WebAssembly really came into the picture. So the idea was to take your high performant functions written in C++ or Rust and then use extensive tool chains. And in this example, you can see that we can compile C++ source code into the WASM module using nscripting. And then once this WASM module has been generated alongside with some other HTML or JavaScript code, this could be utilized inside of your actual application, inside of your front-end application to be able to utilize that WebAssembly module and run it inside of your browser application. And that is how you can basically run your C++ code, or for that matter, any other code that can be compiled into the WASM bytecode, and in order to make your applications or browser applications more performant. And this is how we can also actually run machine learning inference inside of the browser using TensorFlow.js. But of course, the ecosystem for WebAssembly does not just get limited to the browser itself. There are a lot of different applications today, Chrome, Figma, and Microsoft Flight Simulator, even Google Earth. And of course, there are a lot of different other applications that you'll find outside the browser as well. So today, it's no longer an efficient, portable, low-light bytecode just for the web. In fact, the number of use cases for WebAssembly outside the web are far more today as compared to inside the web. So here's an example for that, and this is the State of WebAssembly report, which is a very popular report that is conducted every year, where it can be seen that today the WebAssembly usage outside the browser is being seen a lot more. So whether it's used in Python, containerless, or even creating like serverless applications, you'll find the use of WebAssembly more. And here's another graphic which kind of showcases how people are actually utilizing WebAssembly. So you can see that the usage for WebAssembly on IoT, serverless, and even containerization, that's basically on cloud side, it's actually increasing, whereas the usage for web has decreased as compared to 2021. And this rate will continue to be seen even in 2023. And there are a lot of different types of ways in which WebAssembly can be used outside the browser. And here are some of the supporting platforms. So first is basically the WASM runtimes that allow you to run and execute your WebAssembly bytecodes or binaries outside the browser as well. So these are some of the runtimes that you can see, including WASM Edge, WASMer, WASM3. Again, these are all different set of runtimes that you can use. Then also there are a lot of different platforms and startups that have basically utilized WebAssembly at its core, and they are utilizing them for creating their entire end-to-end entire end-to-end startups. So including Fermion, which basically has an open source project called Spin, which can be used to create serverless microservices based on WebAssembly. Then we have Wasm Cloud that allows you to create cloud-based WebAssembly actors. Then we have Suboptimal that basically allows you to create PaaS, or that's platform as a service, with the help of WebAssembly. And now kind of let's see that outside of the browser, where we understood that yes, you could use tools like mscripting that allow you to convert your C++ code into the WASM module and then use them alongside inside the browser. So how could you now utilize WASM with the help of Node.js? Because we know that Node.js is a very popular server-side technology that allows you to create APIs and build web applications, right? So now we'll understand how you can basically empower, or you can up the performance of Node.js with the help of Rust and WebAssembly. So as we know that Rust as a programming language is a very highly performant language. So the idea is to basically utilize both Rust and WebAssembly, and in order to execute some of the functions that you can run inside of Node.js that would be more powerful if you ran them with Rust instead of directly running them in Node.js. So before that, we'll also understand some of the benefits of actually using something like the WebAssembly virtual machine, which is being accomplished with the help of the WASM Edge runtime. And again, one of the biggest ones is that it does provide security, and it's also extremely lightweight, as we understood the benefits of actually using something like WebAssembly. And it is also highly efficient because it provides near to native performance because of the bytecode, it also uses something known as ahead of time compilation. So something like how Node.js uses just-in-time compilation, WebAssembly uses ahead of time compilation that provides performance benefits. And it also provides runtime safety because of the security sandbox model that is provided with the help of WebAssembly. And it's of course optimized for being able to run server-side applications. So this is the proposal that how you can use. So of course you'll be using Node.js, and that uses JavaScript out of the box for providing ease of use and the extensive Node module support and packages support that you get with Node.js. Whereas you use Rust for its safety and performance, and you use the WebAssembly runtime environment in order to provide the portability and the safety that comes with WebAssembly. So this is how the entire architecture would kind of look like. So you would have basically your JavaScript applications with the Node.js runtime. Now, of course, at one hand, you'll have your typical Node.js runtime that's based on C++ that will run your actual Node.js application. And you'll also have your separate WebAssembly virtual machine that will basically utilize the programs written in the Rust programming language that get compiled into the WebAssembly model, and then they will be run together. And if we kind of look like how this entire architecture would look like, so the idea is that you'll have your main Node.js function or your application still running. But what you could do is that you could take some of the more high performant functions that you would typically run in your Node.js application, but rewrite them and write them in Rust. Those functions written in Rust will then get compiled into the WebAssembly bytecode, and that would be responsible for actually executing those functions. And those functions then can be called upon by the Node.js application in order to run those functions. So you will basically run your both Node.js application and your WebAssembly virtual machine side by side, and the Node.js application will communicate with the virtual machine, like the WebAssembly virtual machine, in order to run those high performant functions and run them very quickly inside of your Node.js environment. So in order to get started, you would definitely need some tools, and that basically includes, let's say, a Linux distribution. You'd also need to install the Rust programming language, have Node.js installed, and then have the WasmEdge runtime that will help you to run the WebAssembly bytecode, and then utilize that with the help of the Node.js. And then we'll also use the Rust Wasm compiler that allows you to compile your Rust modules into the WebAssembly bytecode. Now, in order to get started, here's an example where you can visit this repository and basically clone this repository for the WasmEdge Node.js starter. And we'll also take a look at how the Rust function is written, how to compile it down into the WebAssembly bytecode, and then, of course, run it alongside your Node.js starter code. So before we jump into the actual Node.js starter code, let's head over to our VS Code. And over here, I'm running a GitHub code space. And I have my WasmEdge Node.js starter that I have already installed. Now, if I quickly take a look at first, initially the lib.rs file. Now, this is the main file that will be of use to us, right? Where basically we have a simple Rust function where the Rust function is simply taking a string that we will pass as an argument, and it will simply just return hello and whatever we pass as a result, right? And this will be used. Now, once we used the Rust compiler, that's basically using the Rust Wasm C compiler toolchain, this program will basically be used to generate the WebAssembly bytecode. And this bytecode then can be used inside of our Node.js function. So if you take a look over here, and if I go to my app.js function, which is basically a Node.js app that I have written, you can see that once we successfully generate the WebAssembly bytecode from our Rust module, it will also generate a starter code, which is this WasmEdge Node.js starter library, which will allow us to basically go ahead and parse the WebAssembly bytecode, and that can be included inside of our Node.js function. And then, of course, we are just using the standard Node.js function to create a server, which will be running on port 3000. And it will use this simple command, basically our URL, and it will run on port 3000. And if we send, let's say, any query alongside that, that's basically our name, it will utilize that same function to basically print hello and whatever query param that we are sending with our function. And once this is successfully done, then you can actually test it out and send in any query, and the response that you get is hello with that query object name that you're sending inside of your application. So this way, of course, this is a very simple example of like a hello world example, but you can think of other ways in which you might have a more highly performant function that would be written in your Rust module, and then you compile it down to your WebAssembly bytecode, and then run that alongside your Node.js server to be able to execute that inside of your browser. So this is the example of how you can basically take your Wasm code and then run that alongside your Node.js application to make the performance of your Node.js applications faster, because of using the efficiency and the compilation time that it takes for being able to execute your functions with the help of WebAssembly. Now, of course, you can also use WebAssembly not just for Node.js outside the browser, but you can also use it for serverless computing. Because typically, whenever we talk about like serverless functions, we are usually thinking of writing these functions in JavaScript or Python. But WebAssembly allows you to write much faster serverless functions using WebAssembly, again, because of the smaller footprint. And one of the other benefits that also comes is the portability. Now, if you were to run these serverless functions in JavaScript or Python, they may be dependent on the platform or the environment in which you actually execute and run them. But that issue is overcome with the help of being able to run these on WebAssembly. And of course, these are also much more secure in terms of being more performant. And in fact, a lot of platforms like Vercel are actually utilizing WebAssembly edge functions in order to quickly deploy your applications on edge locations. And today, you can actually go ahead and run any of your applications and deploy them using the edge functions powered by WebAssembly. So we'll take a quick look on and see how you can actually run WebAssembly, as a function as a service. So here is an example of such kind of a use case where you can see that this particular tutorial is basically using the MobileNet TensorFlow model, which is a very popular machine learning model, and it is using the MobileNet TensorFlow model to basically deploy this serverless Rust function that is being deployed to a server, a serverless function, and then you're basically just utilizing this HTML function, and it will call that serverless Rust function and then execute to basically determine that, okay, what type of model is being utilized. Now, if I also quickly showcase and demonstrate like an example for this, I will quickly go ahead and go specifically to the JS food, where basically what I've done is that here when we call this particular function, and for that I'll specifically showcase the demo for the being able to actually run, like, let's say a JavaScript function using the quick.js. And this is specifically what is happening over here is that we are using the quick.js runtime, right? We have like V8 as a runtime engine. Quick.js is also a JavaScript runtime engine, but of course it is much more smaller as compared to the standard V8, and it is very efficiently programmed to run for WebAssembly applications. So I'll quickly go ahead and go to our JS food example. Now, in this example, if you take a look at the main .js file, what is essentially being done is that we are using TensorFlow, which is a machine learning library. And in this case, we are having a quick.js WASM file, which will be basically utilized to actually do the machine learning inference for us, right? In this case. So this is what we are going to be doing. And we'll simply just go ahead and run this code where we are using the WASM TensorFlow Lite, which is basically an extension dedicated for WebAssembly to run with machine learning. And if I quickly demonstrate over here by running the main.js file and providing our WASM bytecode, it will run, and you can see that in this case, the example image that I provided to my function, and you can see the image over here, which is basically this food.jpg file, which is basically hot dog, and it was able to, in a matter of like milliseconds, it is able to give the label and basically predict the response, and then also provide the confidence as well, right? Now, of course, if you wanted to basically, let's say, go ahead and deploy this application or an example application like this on, let's say, a Vercel, right? To probably create some kind of an application like this. There's also a similar example where you can basically go ahead and deploy this same example as a function as a service. So for that, basically the code that I'll showcase to you is to basically go ahead and, again, the main thing that we're doing is that we're basically building our Rust program into the WebAssembly bytecode. So if I go specifically to the function as a service over here, and over here, if I go dedicatedly to the API, you'll find that I have a dedicated function within my main.rs, which is basically, again, doing that machine learning inference for us. And once I actually build this successfully, it generates this classify.wasm file, which has been generated from our Rust module. And now what you can do is that you can go ahead and actually deploy this function as a service. And for that, you can see that over here, I have a index.js file, which basically showcases that you can use the Vercel runtime environment. And this will basically utilize the select and photo, like where we are basically selecting that photo. And we can go ahead and actually successfully run this application. And if I actually go ahead and go to this particular repository and just, if I try to, let's say, go ahead and run this locally, I can also try to do that because we have already successfully built our application. So I'll go to our fast, which is our function as a service. And then I'll just go ahead and do an npm install to install all of our node dependencies. And then we'll just try to run this locally. And then, of course, once this runs locally and you've tested it, you can go ahead and deploy this to Vercel as well using Vercel deploy, which will deploy this as a serverless function. So you can see that how easy it is to actually create either, let's say, being able to run WebAssembly on the server side with Node.js, or even create serverless functions. So now, since it has run successfully, let's go ahead and do an npm run dev in order to run this. So we'll go ahead and actually just stop one of my existing ones, and I'll run this again on my port 3000. and let's go ahead and see how this perform. So this is our actual application where we are basically using our Rust function compiled into the WebAssembly bytecode to run it as a function, as a service, to be able to execute it. So here you can see that this is like, photo, and what we'll do is that we'll select a photo and see what answer do we get, right? So let's say that I'll select this photo, and we'll basically use classify with wasm in order to like generate what response do we get. And for that, like, we can also go ahead and take a look at the server response, or like the server in which we'll basically get. So I'll go ahead and select a photo, and let's go ahead and let's see what response do we get. So again, like, this is being powered by Vercel. I'll simply go ahead and refresh this once more to see what response we are getting, so that you can also see like the response from the server. So I'll open up the network response as well, and I'll clear this out. Let's go ahead and select a photo with the food item. So you can see over here that we have got our food item, and of course now you can go ahead and classify this with wasm to basically like, exactly get a response like we got initially when we ran just our TensorFlow app, like, TensorFlow implementation while running like a JavaScript function. So you could see that by this specifying our main.js file, it is using the quick.js runtime environment. That's basically a runtime for JavaScript in order to run or execute that WebAssembly file. And similarly, in this case, we have generated a function where inside of our Next.js application, we have our main.rs file. And this inside of the target, you can see that it generates the wasm file instead in our classify.wasm. And then you can go ahead and deploy this application as a function as a service in order to be able to run your machine learning inference with the help of WebAssembly. So that is a quick demonstration for like the serverless capability with the help of WebAssembly. But that's pretty much it for today's presentation. And again, in case you have any questions, you can reach out to me on How to Develop, and I'll be more than happy to take up any questions right now. So what it kind of showcases that WebAssembly is a really amazing technology to be able to run not just on your browser, but also support JavaScript outside the browser, whether it's with serverless functions, and whether it's with being able to run with Nodejs to make the performance of your Nodejs applications much faster. But with that in mind, thank you so much.